what I want to do today to introduce you to like a journey. Like when you train your fancy machine learning model, there is so much more that happens before you get the data. And often when you get a strange result, you just say, well, the model didn't work. Okay, sometimes the model didn't work. But often people don't really realize how the images are acquired, how they're formed, how they're processed before they get to you. So I want to give this presentation going from pixels and how each pixel is acquired and processed to insights. Probably I'm not going to be touching much about machine learning because Claudio, Michael, the other day already introduced some of the concepts that are pretty common. So I'm going to skip that, only mention when it's necessary. If it's not, I will just move on. If you guys have any questions, just raise your hand and let's chat. Actually, I want you to ask questions. If you will not be asking questions, I will stop and ask you questions one by one. Okay, so this is the agenda. I have like 4 parts, and try to divide in something that made sense. First, we're going to be talking about why the images are not created all equal, and what does it mean? What are the concepts like revisit, spectral and spatial resolution, agility of the satellite, and geolocation accuracy. Then I will touch on what is called ARD, analysis ready data, which is a framework that's used to include like several pre-processing steps that are generally necessary for you to do machine learning after. Okay, before I do that, I don't know if you guys are familiar with Maxar, previously known as Digital Globe. We currently operate 4 satellites, WorldView 1, GeoE1, WorldView 2, and WorldView 3. We retired Iconos and QuickBird. Those were satellite launched early 2000. Those were the first high-resolution commercial satellites, like 50 centimeter. And we also retired WorldView 4. There was a failure in the gyro, and we have to retire it. This year, we are launching 6 Legions satellites. 4 have been already launched, and we are currently commissioning them. And the last 2 are going to be launched in the next few months. The nice thing about Legion is that it will enable us 15 revisits per day. So that means that throughout the day, we'll be able to collect multiple images at different times. And so this opens up really what is known as like human patterns of life. You can see how things move through the day. And because of that, we need to understand, again, how the images are formed and acquired so that you can apply your machine learning models. How many of you have seen like a spreadsheet like this with all the specs? Good. So there is a lot of information here that often is kind of like overlooked. And so, for example, the orbit. This is for Legion. And one thing that you can see is that we have 2 different types of orbits. There's a sun-synchronous and mid-inclination. Sun-synchronous, the satellite fly over the poles every, I think, 90 minutes or so. Mid-inclination means that they fly like this. So they don't go over the poles. And because of that, you get like multiple revisits per day. So the type of orbit is really important. It's really important because when you acquire images through the day, the shadows will move. And also because the satellites are agile, they will also change the view angles. So you really need to understand the geometry of the collection. Otherwise, if you're going to be doing like building detection or whatever model you're trying to develop, you will see things moving in a way that might appear out of control. So that's revisits. Spectral resolution. Most of the satellites these days, they have either like 4 bands or 8 bands. Generally, there's a panchromatic band with like higher resolution, but much wider spectral response. And then other spectral bands, generally in the order of like 60, 50 nanometers. In Legion, there are like 2 red edge bands that are like really narrow, about like 20 nanometers. 2 red edge bands will allow better precision agricultural type of applications. Spatial resolution, I think this is pretty self-explanatory. Legion are 34 centimeter and nadir, so looking down. Agility. Mentioned earlier, satellites look straight down, normally, like Sentinel, for example, Landsat. Commercial operators, generally, they have a satellite with agility. So you can tilt the satellite and collect in different view angles, which is really important when you want to open up the collection capacity. Finally, the geolocation accuracy. They're generally they're like 10 to 5 meters in general commercial satellites. That means if I collect a pixel here, I want to make sure that here is actually here, it's not 10 meters away. And there's a really big implication about, for example, labeling. Like if you collect a label from one provider and then you want to export those labels to another provider, you want to make sure that you're looking at the same pixels. So I'm going to go through all those items now in slightly more details and show you what are the implications. And so, for example, we talk about revisit per day. You can see probably maybe with the lights it's kind of like hard, but you can see there are like multiple bands here with higher revisit time, and so here like between Europe, US, we will have about 13 revisit per day. So that means collection from early morning to late evenings. Spectral resolution. The one thing I really don't like about machine learning these days is that people only use RGB. And the reason is because we are lazy generally. Like we just get a model from GitHub and we only use RGB 8-bit data. Satellites have so much more information. You generally have, again, at least a near-infrared band. You often have many more spectral bands. Think about hyperspectral. And so you really want to try to exploit the spectral richness of satellites. Just to give you an example, those are like spectral signature of different vectors, not only from Maxar. But you can see the difference in colors, and I hope that you can see that with the lights. But this is the human eye response. First of all, you can see there's no the blue, green, and red. They are not linear, and so having more information like the 8 bands here, you can see colors much closer to what you actually see from the ground than if you have only like 4 bands, for example. Spatial resolution. Are you guys familiar with NIRS? Okay, so NIRS is generally in the image metadata that providers have, and the NIRS it's a rating. Generally, like 3.4, you can understand. For example, there are like objects, like airplanes, for example, and a NIRS, so like close to 6, you can distinguish different weapons, for example. And so, all providers have this information in the metadata. And it's really important when you do like object detection. If you're trying to detect cars, for example, a NIRS of 3 probably is not going to make it. You want something, I don't know, maybe NIRS of like 5 or 6 or even 7 if you can. But the higher the value, the more possibility you have to detect something small. And this is an example, like car detection. I don't remember where this image was collected, but it was a big parking lot. probably like a car factory or something like that. And what we did was to reduce the resolution from 30 centimeter to 50, actually 60. And you can see that 30 centimeter, we can detect most of the cars with high accuracy. If we go to like 50 and 60, it gets a lot harder. And again, deniers plays a huge role in this. And in general, the collection geometries play an important role. So when you get an image, make sure that has the resolution that you're looking for the specific application. We talk about agility. Do you guys get what agility is? It's basically being able to move the satellite. And when you move the satellite, you can collect images like these. This was collected, I don't know, maybe like 20 degrees above the horizon. So the satellite, let's say the satellite is here, and you're collecting something like this, instead of like looking straight down. When you get collection like this, looks more like an aerial image. The resolution in those kind of images is much more coarser than if you collect a nadir, for obvious reasons. But when you are able to collect with different viewing angles, you might be over, I don't know, Poland, for example, and collect a shot straight to London, for example. So your satellite is flying this direction, and you can collect something really, really far away with some viewing angles. What we did here, this was like September 2022, I believe was when the Queen died. And so we collect every single image that we could over London. And because of that, we were able to see how the crowd changed through the day. For example, this was 11:42, 11:44, 12:37, and 2 o'clock in the afternoon with Worldview 1. And so this is the type of collections that you can expect when you have a visit through the day. The interesting thing, though, is that you can see all the images are collected from completely different viewing angles. Like, this is still the same square, but we're looking from here, or we're looking from, from the castle towards the road, or we are behind the castle in this direction. So how do you account for them when you do machine learning? This is what I'm trying to, to go over with you guys all today. So this goes through orthorectification and alignment. Paolo talked about that yesterday, no, the day before, with SAR. How you get an image, how do you orthorectify it, and what are the implications of having a DEM, like a digital elevation model. And what I'm showing here, so the satellites collect from different directions, right? So the building is projected in different directions. And that's what you're seeing here. So this image is orthorectified. So we already aligned onto the grid. You're already doing a pretty good job making sure that the right pixels in the right position. But you have completely different viewing geometries. And so how do we account for that? Well, if you're trying to do some sort of like time series, not only you need to orthorectify the images, but you need to try to align them. The difference between those two is that if you look at this point here, I don't know if it's a statue or what, but this statue moves like a lot. And here we are trying to align this image on this point, which is now pretty well aligned, but yet everything else is still moving. So again, when you have like a large time series of high resolution images, you need to understand how you can deal with these type of images. If you get labels over buildings, but those buildings move a lot, your model will have really, really hard time training. Geolocation accuracy, what does it mean? Anyone? Okay. She's basically saying like it's where you put the X and Y pixel on the grid, basically. Yes, that's correct. I'll give you another example. You're driving on the highway, and your Google Maps say, hey, you need to turn left, but there is no left, and you go down the bridge. That is geolocation accuracy. What happens is that different satellites have different accuracy, and so if you're over here, you have what is called a C90 of, for example, 100 meters. And 100 meters, if you're in a densely populated area, you don't know if these 100 meters is when you need to turn left now or in 100 meters. And this is the difference in like 5 meters, for example. Think about you need to turn really now and you see the road. Okay, analytics at scale. What is scale? Do you know what this is? Don't tell me a truck, because I know it's a truck. What is that? Who said data center? Great. What is that exactly? You guys are hovering around the concept. That is a ginormous US stick, a really, really big US stick. So what happened? When 4 or 5 years ago we decided to move all our data to AWS, we have about 120, 140 petabytes, and we did some calculation that if we had to move all the data from our data center through internet, basically, it would have taken many, many years to move all our data. And so AWS came up with, Amazon came up with a pretty smart solution. They put a huge, huge amount of memory in a truck, and they drove that truck to our facility, and we literally connected to our data center. And in a few weeks, we were able to move all our data from our data center. They drove back to their data center, and then they download the data on the cloud for us. So when we're talking about a lot of data, that is a lot of data. It's a truckload of data. And you can think that now these data, those images were acquired for the past like 25 years. They're all on the cloud, readily available for you to do analysis. This is an example of image. Nothing very fancy. I don't even know where that was acquired. But generally, this is like 200, 500 square kilometers, 50 centimeter, 30 centimeter data. So once you punch sharp the data, which means you put colors on the black and white on the panchromatic image, you generally get several gigabytes of image here. This is a really, really small collection. This is probably like one city. Generally, like these type of satellites, they're a push broom, which means that we swipe the ground and we collect row by row. And these allow us to collect really, really long swath of data. So this is like about 3 degrees long. Now we're talking about like 6,000 square kilometers. And when the satellite collects it, it looks like a raster like this, right? But once you project it and you put on the grid, the image become like rectangular in this way. And generally there is a lot of like black fill here. And so you go from this number of columns and rows to a lot more pixels. And so when you deal with this data, when you move the data, when you touch the data, you need to have a really, really big machine. We are looking at many, many gigabytes of data. We also offer a product called HD, which double the resolution, so you can get 15 centimeter from us. If you get something like this, punch sharp, 15 centimeter, you're looking at probably several hundred gigabytes, maybe a terabyte of image. And probably most of us, we don't have a terabyte hard drive on our laptops or on our machine. So how would you use this image? Yeah? Tiling. Great. How do you tile it? You just like divide in tiles? What would you do?
Usually only load the tile that you want to see at that time, and the rest is on the memory. You load it in the memory, so whenever you pan or zoom in or out, the only tile that you are adding is loaded
Okay.
on the memory, so it's easy.
She's basically saying that you can just like tile it, and then you can load that part, the processing, and then maybe put out the results, right? Yes, that will work for specific application. If I ask you, for example, to calculate the median of that image, not the mean, the median. The median, yeah, I think. Well, what I'm trying to say is that you really need to think what you're trying to do. Like tiling, that's exactly what people do, but you need to think what you're doing, how you're doing. For example, if you need to calculate the median, you cannot just read each tile, do the calculation, then do like, the mean of the median. That doesn't work. So, correct answer, but you need to put that in a framework where you really need to do like some math before you do tiling. Bottom line, don't do that chipping when you do your machine learning. Like think how you do chipping. We even can collect something really big. This is all Qatar. It's like 26,000 square kilometers, entire state, entire nation. So things can get really, really, really big. So we talked about tiling a second ago, right? So this is tiling. You can have different, different projections. We generally use this MGRS gridding system. You have, zoom 11 on 12, which is about like 5 by 5 kilometers tiles. We generally leave like an overlap so that you can do some fancy math at the edges so that you don't see edge effects. But yeah, that's pretty much tiling, what you're saying. As I say earlier, there are collections that you can do continuously through the day. So you really need to think how you can maintain like a fixed tiling through collections. And when you combine like the geospatial analytics with all these like images and machine learning, you can get then very, what is called like timely pattern of life and human geography analysis. So you really want to understand, for example, if this is like a border, like how many cars are crossing the border, or what is happening in this specific location at this time, and how can you do this through the day. So tiling, great, but we need something a little bit more consistent. The consistency of the data is the most important thing that we can do when we do machine learning. If we get data that changes from collection to collection just because we do a different punch sharpening or because the viewing conditions were different, your machine learning model will have a lot more difficult time to train. It's probably going to be more robust. You get another collection, your model will be more robust, but it would be a lot more difficult to train, and you need to account for that. So what a lot of people have been doing lately is working on this ARD concept. ARD stands for Analysis Ready Data. Most of the providers, including ESA and NASA, they have their version of ARD. And the whole community, both government and industry, have been working on many different ARD standards to the point that we quickly realized that ARD is really, really difficult to achieve. And the reason is your application might be different from my application. And if your application is very different from mine, what makes sense for you might not make sense for me. So settling on a define number of operations has become quickly difficult to the point that we have our own ARD. NASA and ESA have their own ARD. Planet, Airbus, they have their own version of ARD. So when you train your models on multi-provider data, make sure that you check the specs, because each ARD, unfortunately, is still different. What is ARD? You can think about ARD as like a workflow. You have many different pre-processing. You might have atmospheric compensation. You can have orthorectification, punch sharpening, color balancing, bundle block adjustment, grid alignment. Those are all pre-processing that you can do that by yourself. I think most of those are, you know, when Paolo was showing Nest the other day that, you know, he was going through all the like SAR calibration, SAR orthorectification. There is pretty much the same here in the optical world. But how you do each of these tasks can have really, really, really big implications on what is the final product. And so when you get a product as an ARD product, make sure that you check how, for example, atmospheric compensation is done and how the orthorectification, the punch sharpening is done. What is the color balancing? Color balancing is necessary if you use the 8-bit data, because most of the satellites have at least 11 bits. So how do you go from 11-bit to 8? How do you compress the dynamic range? All these are very big implication where the histogram of the image is. And if the histogram is shifted, then your model might or might not work at all. So again, you can think about ARD as a time series stack of data. You know, once you have all your tiles, you can stack them together and you have a common standard across all those images. So this is just an animation to show that, you know, you start with an image and then you extract buildings, you can extract roads, you can extract a lot of information. And generally you have like different steps here. You have the tasking of the satellite, you have the collection of the image, you have the downlink, so from the satellite to the ground, and then there is pre-processing and delivery. ARD covers only those two steps, all the pre-processing and how the image is delivered. Is it delivered on an FTP, an S3 bucket? Where do you get that data? Is it just a TIFF? Is a cloud-optimized TIFF? So all those aspects should be covered in an ARD format. But unfortunately, not all images are created equal. And so think before you start using data, like what is the collection of that data? It's really, really important. This is just like another animation, what I was saying earlier, just like a stack of data. You can get a long time series, like 30 images, 50 images. You can stack them together. You only have the area that you're interested in, generally, you know, 5 by 5 kilometers. So you don't have a ginormous image. And that should fit in the memory of your laptop. So it will allow lower storage cost and also faster processing, because you don't need to go through the entire image. Okay, so this is almost the end of part 1. In part 2, we're gonna do a very deep dive about atmospheric correction, atmospheric compensation. Then part 3, we're gonna be talking about orthorectification alignment and why things shift. And then there's gonna be part 4, which is just how do you go from pixel to insights. Talking about now just the radiometric aspects of the image, which means like the colors part. How do you make sure that the colors are actually correct? And to do this, you have to have a well-calibrated sensor, and you need to have the effects of the atmosphere removed. You know, the sky is blue, and that really changes the color when you go from outside of space through the ground. So basically, atmospheric compensation as a first approximation is removing the blue part of the atmosphere. So that's what we're going to be covering now, radiometric aspects. The part 3 are going to be the geometric aspects. Okay, talk about satellite calibration, and then we're going to be talking about atmospheric compensation and some applications. And let's see how far we go today. We might want to skip this if we're out of time, but if you're curious, I can go over that. So, satellite calibration. For the color part, for the spectral part, how do we do that? It's relatively easy. We have big tarps. Those are like just plastic tarps. And they're calibrated. These are 52%, and these are 3% target. And because WorldView 3 also has SWIR, the shortwave infrared bands, we also have one tarp that is targeted for SWIR applications. But in general, we deploy those two tarps, which are those one, and you want something very high in reflectance and something low in reflectance. What we do is we measure those targets every single time that we do collections. And you want to measure those targets because they age. They get dirty. There's a lot of sand. There's wind blowing. So I remember the first year we got like a ton of crickets because they get really hot, and for some reason crickets really like that. And you know, when you have like a fair amount of crickets on those tarps, they change the spectral signature. And when you smash them, the tarps get dirty. So we have to keep those clean, and we need to walk them every single time we do a collection so that we make sure that the geometry is included and the fact that those tarps are aging is also included. So we take measurements on the ground. I think I have some better pictures, maybe, yeah, here. We take measurements on the ground with a spectrometer. That is basically a backpack with a big hyperspectral camera. We do a white reference. So this is I think it's called Spectralon. It's 100% pure white. And this is the most critical thing that we have as an instrument. Like, we want to make sure that this is white. If this is not white, all the measurements that we take are not accurate. So when we do the white reference, we have some weather station here, so we can understand what are the atmospheric conditions during the acquisition. We want to make sure that if you're looking blue sky, if there is haze, what's the water content, temperature, and so on. And we have multiple operators that take white targets. And the reason of this is that we don't want that, you know, someday someone has like a bad day, it's like really sloppy, doing a job not very good, so that we can average all those measurements. And once we do those measurements on the ground, and we have all the measurements of the atmosphere, we use something called a radiative transfer model. There are a couple of versions. There is 6S, which is open. There is Modron, which is, you have to pay a license for it. But basically, those are like a lot of like very, very, very complicated radiative transfer equations for the atmosphere. And what we do, once we know what we see on the ground, we project that on the top of the atmosphere using these. We can also account for the surface BRDF, which I'll go through that later, but it's basically saying that different objects have different colors, depending on where you're looking at. have you ever drive on a sunset on the highway? The highway, it's really, really bright generally because the sun reflects towards you. So the highway or like the road is not gray, but it's really like light gray or even white sometimes, depending on where the sun is. That is BRDF. So once we have that information, we can do the prediction of what a sensor would see in space. So we go from the ground up. And once we know what we measure on the ground in space, we can also compare to what we see from space to the ground. And we want to make sure that those two numbers are the same. If they're not, we need to calibrate. And so all this is basically the description of what I just said. So, you know, if here we measure, I don't know, under 50, we want to make sure that we measure under 50 also here. This is the TOA, top of the atmosphere, modern results. And we need two TARPs, because if you only have this one, or only this one, you know the intercept, but you don't know the slope, right? So you want to have at least two measurements so that you can tie, you can anchor this line and you can correct the satellite. This is a very simple model. There are models that are non-linear. Generally, when the satellites measuring very high response, they saturate. Sometimes you see flare in images, and that's because the satellite have a non-linear response. So we try to measure 3% and 52% because that is the linear regime generally of a satellite. Anything is above like 90% reflectance is very, very bright. So depending on the geometry, you might saturate. Those tarps are very heavy, like very heavy. I think they weigh like 200 pounds, sorry, 200 kilos. So you need many, many students. I think the second year we were smarter and we asked the football team at CU Boulder to help us. And that was so much better. The first year we didn't know those were so heavy and we did that by ourselves. And that was my last year doing that. So we also, this is our facility now. We rent it, we built like a shed and we keep all our instruments there. The first time we went to like a park, like a public park, and the black tarp killed the grass completely because we were there for like 2 hours. That's really dark. There was no air going through and the grass was gone. People were not very happy about that. Okay, I think this is the only thing I really want to talk about calibration. We also do lunar crater. It's one of the Red Rock Valley. Those are the classic calibration sites. We go along with NASA scientists, ESA scientists. We do like big calibration campaigns together, and we do like some cross-reference with like Sentinel and Landsat. We have pretty good agreement. There's a big, big difference. Again, our satellites are agile, so BRDF really, really plays an important role. Sentinel and Landsat, they look down, and we don't see exactly the same thing. So establishing like a baseline is not very trivial. But in general, we are within specs, you know, less than 10%, and we are close to like 5%. I think that's pretty accurate compared to, you know, not doing any calibration or, again, most models, they still use RGB 3-band 8-bit, which basically kills why we're doing this. So use all the bands when you can. Questions about calibration? I need a question because otherwise I'm not going to move. Yes? Okay, there are different aspects of calibration, right? So first of all, we are the company that also built the instrument. So we cannot really send us back to us. It's already with us, right? But this is kind of really trivial for this type of calibration. We're talking about a spectral calibration, right? So we know that those TARPs have 3% and 52% reflectance. What we need to do is just that when we get the data from the sensor, we need to measure 52 and 3%. If we don't measure that, then we calibrate it. We are the owner and responsible for giving you the right data, right? There's not like, oh, send them back the oscilloscope to someone that built that. We build those sensors. We operate them. We need to make sure that they are correct. I think there was another question. Yeah.
My question is about the seasonality, like when you do the calibration, does it impact on the geometric correction, and how would that actually work?
So the question is, does seasonality have an impact? Yes and no. So first of all, in Colorado, during winter, we are based in Colorado, like almost like 2,000 meter elevation. So winter is really, really cold. When I say really cold, I mean minus 20, minus 30. So we really cannot go outside and do this. So we mostly focus between mid-May to end of September. That's when it's reasonable to be outside. October, we might get snow. End of May, we still might get snow. So the summer is really the core time. Now, summer is also when the sun is highest in the sky, so we get more energy, and the more energy, the better. So in the grand scheme, summer is the best time to do this. What we need to really do is to take the measurements at the right conditions. So if the satellite is collecting at 45 degrees of nadir, we need to collect data with the spectrometers at 45 degrees. Because again, otherwise you have BRDF effects. So because we do this, then wherever the sun is, it's not really important, right? Because we collect the data in the right way to do it. But in the summer it's better because you have more energy, because the sun is more intense. Okay, atmospheric compensation. A lot of people call it correction. I have a long discussion with a colleague where he convinced me that the atmosphere is not wrong, so it cannot be corrected, but it can be compensated for. So I'll try to use the word atmospheric compensation instead of correction. If you hear correction, it's the same, but it's grammatically wrong, I was told. This is one of my projects. I work on this for, I don't know, almost 10 years, 8 years probably. And so I have like a ton of slides, which I don't know if you're going to be able to cover everything, but if you guys have questions, we can talk about this during the coffee break. But in general, atmospheric compensation is the algorithm that gets you to what is called surface-reflectance. Surface-reflectance is what you measure on the ground with, for example, a spectrometer. But again, there is this thing called atmosphere in between the sensor and the ground, and what you want to remove are the effects of the atmosphere, which is not just the blue color, which is called Rayleigh scattering, but it's also aerosols and water vapor and all the particulates in the atmosphere that you want to remove. And we talked about digital numbers the other day with SAR. Digital number is basically the same in optical. You have like a storage container, and how do you translate the the electric signal from a sensor to pixels? That translation is the digital number. In ACOMP, atmospheric compensation, is the process of converting a digital number into surface reflectance. So when you get a value, that value has a physical meaning. Main advantages, you want to remove the effects of the illuminations because the sun is in different positions. You want to remove the effects of the again, the atmosphere, and you want to do some cross-sensor processing, if you're not on the same baseline, you cannot do cross-sensor processing. ACOMP, which is our atmospheric compensation software, it derives the AOD, the aerosol optical depth, and water vapor from the same image. So we are able to have AOD maps of 2-meter posting or less, and they allow us to remove effects of, like, for example, cirrus clouds. Not clouds, cirrus clouds. They're different. This is an animation. It kind of like goes back to what you were saying earlier about the stereo collections. Because those satellites are agile and they can move, you can collect multi-shots over the same target, which is an extreme case of like stereo collection. Stereo collection is either like 2 or 3 collections. I think here was during the commissioning of WorldView 2, so we can play with the satellite as much as we wanted, and we collected, I think this was like either a 30-shot sequence or a 50-shot sequence, something like crazy. But if the lights were off, you will see that the more off nadir angle you are, the more the image looks blue. Wait for it. It's getting more and more blue and hazy, you see? It's really difficult to understand what's going on. Those are the effects of the atmosphere. The more you're looking off nadir, the more atmosphere you're going through, and the more atmosphere, the more blue color you get. So again, when you do machine learning, if you get a shot that's nadir and you're comparing to something that's very off nadir, you really need to go through self-reflectance. Otherwise, you will get everything that is blue. Also, the histogram is a lot narrower. So instead of having something where you have a nice Gaussian shape or whatever, everything is very, very narrow because the atmosphere really shrink the dynamic range. So you want to use self-reflectance to make sure that you use the entire dynamic range of the sensor. Okay, so sensor measures electrons, actually photons, and photons are translated to electrons, right? And then those signals are put into a storage container called digital number. Digital number is not a physical quantity. When you read 800 counts or 1200 counts or whatever you want, if you're an 8-bit, you measure like 200 counts, that does not have any physical meaning. And the reason is that sensors, they have an exposure knob that you can change. And so if you collect images over the same target at different times, you might get over water, for example, 200 counts, but then you change the exposure and you might get 500 counts. You're looking at exactly the same water, the same time, the same everything, but because you change the exposure, that number is different. So you want to use at least TOA reflectance. TOA reflectance is the top of the atmosphere reflectance. It's basically what a sensor measures out of space. And this is really easy. You know what the radiance is? The radiance is basically the digital number, and there's a factor that it's in the metadata that you can use to multiply your number. Radiance is a physical quantity, but it is not normalized. And you want to normalize for the irradiance of the sun and multiply here by the cosine of the solar zenith. So where basically you want to make sure that you know where the sun is. Once you do this very, very simple calculation, you are in TOA reflectance. Those are units. It's a quantity that goes from 0 to 1. 0, no reflectance. 1 is 100% reflectance. And you can compare the TOA reflectance from Maxar to the TOA reflectance from Sentinel and Sentinel-2 and Landsat, everyone. All the satellites are the same. It's TOA reflectance. You want to go one step further, you can correct for the Rayleigh only scattering. Basically means I want to remove the blue color of an image. And this is what L up is. That's the upwelling gradients, this term here. So if you do L minus L up, and you use the same formulation here, you get really only reflectance. If you want to be really, really fancy, you can go through all self-reflectance and do all these calculations once you know the AOD and water vapor information and a bunch of other factors, and also Modron. And so it gets really complicated really quickly. But you can see some effects here. This is theoreflectance. You're out of space, everything is blue. This is still better than just working digital numbers. Like, at least this is normalized in some way. If you do Rayleigh only, you kind of remove the bluish color. You can see this lake is more blue than over here. With surface reflectance, you get through colors. So those two are really, really easy to get. This one, you need to do a lot more. But where you see a lot of difference between those two and this is when you have very, very hazy conditions. There is a lot of haze here and some cirrus clouds and some actual clouds. Cirrus clouds are opaque. You can kind of see through. And then you have those popcorn clouds, which you cannot remove. You cannot see through clouds. But self-reflectance basically maintains some stability of the signal. This is Beijing. In north is actually in this direction, but the image was too long to put in a slide, so I have to rotate it. What you can see, this is the city. Here's the mountains on the east side. There is a lot of atmosphere here. We can retrieve the AFD map, which is this one. This is the information about the atmosphere, the haziness of an image. Once you have this information, water vapor, you can correct it. And one thing that I really like is that, generally when you're on a mountain, you have cleaner air, and this is reflected in here. You can see there is the AOD here is much, much lower than over the city. And here's Pavia, north of Italy. Again, north is here. Those are the Alps. And beside this area of haze, look, there is here some haze, and here there's a valley with a town. And when you calculate the AOD map, you get this that's been completely removed. But also you can see that there is some haze in this valley, which is here. And that is because there is a city there, so they create their own pollution, I guess. Better quality, visual quality. Those are all 8-bit images. And you can see how, even though there is a lot of atmosphere going on here, the signal across those images are very similar. So you get stability. Things don't change dramatically just because today is a bad day and there are clouds. This is a time series over Hanoi in Vietnam. There is generally a lot of atmosphere in this region. And you can see here the signal is a lot more stable than over here. Like here, for example, there is some atmosphere. Okay, biophysical variables. I had a few slides because some people here have done some vegetation stuff, so I thought that this was interesting. I'm not going to go through this again, but the NDVI is one of the easiest things that you can calculate from a satellite image when you have near-infrared data. And the higher the value, generally between 0.2 and 0.8, the healthier the vegetation is. It's textbook. But when you take measurements, and this was, I don't know, some grassy area that I measured several years ago, you can see different things. So this is the black line is what I measure. So this is what grass looks like with a spectrometer. And if you use theoreflectance, the values are not super accurate, and they're less accurate the more you go to shorter wavelength. Do you know what color is this? 400 nanometers, 450? What? Blue. The sky is blue, right? That's what this is telling you. Yeah, the sky is blue. And it's not red. That's why it goes down really quickly. But this is the contribution that you can remove if you have a Rayleigh-only correction. Now, if you use theory reflectance, you also notice that there is something going on here. And there is a really big water vapor absorption region around 900 nanometers. And so if you don't account for water vapor, your near 2 and red edge band will not be very, very accurate. And so if you calculate NDVI from theory reflectance, you get about 80%. If you work in surface reflectance, you get about 90%. So there's a pretty significant difference. So again, working surface reflectance will allows you to do much more accurate analysis of your data. Questions? No. So this is the NDVI map of this field, and from looking at these, you will think that those two fields here have different health status, with this being better water maybe than this one, because the NDVI is lower here than here. In reality, what you're measuring here is just the fact that this crop is darker than this, for the most part, because once you do the same NDVI using surface reflectance, you get something like this. And in this image, you should see, for example, that here there is a stressed vegetation, which was not very obvious, just looking at those images. So bottom line, use surface reflectance where you can. Sentinel-2, Landsat 8, 9, they all come with surface reflectance. Doesn't cost you anything to just select the right product. Oil spills. This is also an interesting one. So this is the Louisiana oil spill in, 10, 15 years ago. If you use theory reflectance, you see something like this. Actually, this is radiance, but it's the same thing. If you measure surface reflectance, the spectral signature is really the opposite. Can you tell me why? What's going on here? Why do we have most of the energy here? Someone say something. What? Well, it's the same, right? Actually, we are measuring this point, this is oil. But why this is going up in this direction, this is going up in this other direction? Exactly, because the atmosphere is blue. This is TOA, right? So you have a lot of atmosphere, and the signal of the atmosphere is much higher than the signal of the oil. And so if you do not remove the effects of the atmosphere, you cannot measure this point accurately. So again, really remove the atmosphere when you can. The nice thing is that you have measurements from people, and then once you have those measurements, you can infer what is the amount of oil in that location, which was about 25 of these oil emulsion aerial fraction, which I have no idea what it is, but it's some measurements of oil content in water. You cannot do this if you don't work in surface reflectance. And so this is RadarSat, like oil spill and SAR, is one of the killer applications. Like if you have a SAR image, oil spills are really, really easy to do. But you can get also like optical images. And the nice thing about optical images, you can get now oil content because of those curves I showed you earlier. And I believe that you can do something similar with SAR too, but not an expert. If Paolo is here, no, it's not. Yeah, he's here. Can you do measurements of oil in? In some instances, yes. With optical, you can measure the amount of oil too. And the nice thing, if you do some data fusion of these, then is where you really can do a very well characterization, especially consider that SAR you can acquire night and day, so you can do a very detailed time series, and with the optical you can understand how the oil is moving, the one is afloat. Time series, time check, 20 minutes. We might be able to finish. I played, with some time series over Denver, Colorado. 21 images collected through, different viewing angles. And this is the position of the sun. So you can see that through the year, the sun changes position. So those are like summer collections, those are winter collections because the sun is much lower. And at that time, I had so much fun to define labels on 22 different classes. 22, something like that. Different type of grass, different type of rooftops. I even included like a pitched roof. So sometimes roofs are like flat, sometimes they're like this, right? And can we understand from spectral signatures if a roof is pitched or not? The answer is yes, and I'll show you how. But first, you guys have 10 seconds. How many changes do you see in this image? That's like the posters yesterday, 1 minute. White building on the left. This one, I guess. Oh, there's this one too, I guess. Yeah, because this was summer. Yeah, after, the end of summer, they generally close the pools. There is more vegetation. Okay. This is a very small image, right? Think about doing this at scale. And think about doing this on hundreds of images. So you can have some machine learning model to do that. When I was young, PCA was really famous. And this is really easy. You don't have to do anything. You don't have to do training or anything. But if you take the second component of PCA, you basically map the differences, right? So if you do that on digital numbers, you get basically everything is changed. And the reason is because there is a bias difference between those two collections. One thing that I didn't say was that those two collections were from completely different viewing angles. So not only there's a time difference, but also the collection's geometries were different. Now, if you do the very same PCA analysis to second component with surface reflectance, now you get something like this, where all the changes are much, much easier to identify. Those were the changes. What is going on here? Why do we have, so this is a time series over the same object. What is going on here? Why do you have these huge, huge variations? Normalized DN is basically a DN divided by the maximum number, so everything is between 0 and 1. The what? Yes, so I'm also reporting the AOD, which is the A's in an image, right? What you can see is that there is some variability in the A's here. So again, when you look at normalized DN, when you look at DN, time series don't make any sense. You have differences because the exposure is different, you have differences because you have different illuminations, different atmospheric conditions. So this is useless. You cannot really do anything with this. This is a lot easier to understand. And it's a lot easier because this is surface reflectance. What are we looking at here? Francesco is laughing. What are we looking at here?
Why are you laughing?
I don't know. Okay, so we have removed the effects of the atmosphere. So there is something going on here, right? Any guesses? That's a pretty extreme. You go from 40% reflectance to 5, what?
Has a very low reflectance.
Yeah, and that is bright again. Things age. Things age. These are rooftop that through the years between 2002 and 2006, 2007, it got dirty, and to the point that we're redoing it. And so in this time, they were working on the roof, and then they finish it. It's new again. And you can see here how there is a downward trending. That's because things get dirty. When things get dirty, they get about 15, 20% reflectance, because that's the average reflectance of Earth, more or less. So there is a convergence, and then, boop, new roof. And here I just want to say that, there is some correlation between the AOD and the signal. So again, this is absolutely meaningless. Don't use it. Okay, what color are we looking at here? This is another object. What is the color of this object?
Yellow. Because blue plus green is yellow, no? No, I'm kidding.
Could be. Red, okay. So this is actually kind of like misleading because I just wrote reflectance. I didn't say it was theory reflectance, surface reflectance. So it's really not easy to understand. But one thing that you can see is that there is some variability in the atmosphere. And look at the blue band. Once you look at the blue band, and if you see that there is some correlation between the AOD and the blue band, then probably you're not using surface reflectance. And in fact, there was some correlation here, right? It's visible. Once you're working through surface reflectance, now you see there is almost no correlation to the AOD. And now you can really tell me what color is this object. What? It's a red object. Like near infrared, we cannot see near infrared, right? So we're not, I don't know what kind of animal. So the highest band is red. So this object is red. And what are we looking at now? What is that? So this is what's called a BRDF type of measurements. And it is the same object. So we know now that it's red. But there is also like a lot of variability here. We go from 20% to like 25%. And so if we plot those values, we see that there is some distribution. Like this side is 24%, so it's brighter. This side is more like 22%. Why? Yeah? Closer to the sun. Yeah, you're going somewhere.
There's like a triangular shaped roof.
Correct. That is a pitched roof. It's red, and we know that it's not flat. So the sun is here, right? So this is the illuminated side, and this is the shaded side. So just looking at the spectral signature, you could have identified most of the properties of this object. We talk about BRDF. which is similar to the scattering mechanisms that we talk about SAR, kinda, not really, but it's something similar. There are different type of scattering, but look at this, for example. Like, those images were acquired like 5 days apart, and like this changes a lot. Look at this, brown, light brown, dark brown. What's happening here is that you have completely different viewing directions. And because of that, BRDF plays a huge, huge role when you do these type of applications. And BRDF really depends on the material and the geometry of that material. If you're like gravel, will be different than if you have very flat surface. Do you guys know what this is? Exactly, that's vegetation. We have like 50% reflectance in the near, right? So must be something really, really dark and very bright in the near infrared. This is excited vegetation, but we see we go from like 40% up to almost like 70%. And if you plot that vegetation, again, in a BRDF type of style, you can see that here you have the illuminated side of a leaf of grass, right? Whereas over here, you're on the other side. And so the grass looks darker. So when you analyze time series, you really need to understand the geometry of the collection. And if you understand the geometry of the collection, you have done 80% of the work that probably was someone asked you to do. And there's no machine learning here. Like, this is the beauty. It's just physics. Once you understand the physics, the application of machine learning would be a lot easier. We can go even further. We can actually do machine learning, like very simple machine learning, but we can do machine learning. So there's this model called RPV. Here's the publication. The RPV modeling decomposed the spectral response through time in different components. It's the amplitude, the shape anisotropy, and the asymmetry factor. Basically tells you what is the shape of this BRDF object, okay? Those 3 components. Now, if we analyze time series over those 5 grass surfaces in DN space, it's really, really difficult. Everything, there is so much overlap between classes that it's really not possible to define many clusters. And I think I used like random forest for this. This was like 15 years ago. And again, don't go very complicated if you don't have to. Here you can say it's vegetation, which I don't remember who, someone of you say, yeah, that's vegetation. Yeah, that's easy, right? But can we distinguish between a stadium, golf, and parks? You know, those are different, they're different type of grass. If you work with surface reflectance, you can identify at least 2 clusters for the most part. And so you can distinguish between stadium, golf, like fairway and green, and the park grass. Probably, you know, these are much more well-maintained than like a state park. Now, if you do the same by using the RPV decomposition, the first component, which is similar to what the surface reflectance is actually the amplitude, right? So it's kind of like really the same. You can kind of like cluster those objects in the same way. And probably, I don't know if you guys can see the colors there, but there are like 2 clusters here, 2 bubbles. You can probably see them better. If you use the K value, which is independent from these, right? So now we have those 2 other clusters. And so when you put together these and these, you can distinguish at least 3 other classes, like these, and these. And when you add the 3rd factor, you can distinguish all 5 of them. So when you put this into, sorry, want to take a picture? Yeah. We're going to distribute those slides. So when you do this analysis in the end for those 20 plus classes, you get about less than 50%. which is not bad. Like 22 classes is pretty difficult, especially because some of those classes were very, very similar. If you surface reflectance, which again is almost free for you, right? You can get this from Landsat, from Sentinel. You get a bump to almost like over 70% accuracy. Then if you have a large time series and you do an RPV decomposition, for example, with considering all this spectral information, the time information, and the angular information, then you get to like 85% accuracy. So again, there's nothing fancy about these models, very basic, it's random forest. But you go from 50 to 80 in really, really easily. Precision agriculture. I'm gonna take 5 more minutes since you guys were 20 minutes late. Gonna go fast on this, but I'm analyzing this field. And if you use like DN, it's really difficult to understand what you're looking at, right? Everything is mixed up, it's a mess. If you with surface reflectance, it's still a mess, but it's a lot easier to understand what's happening here. I'm not gonna ask you what's happening, but I'm gonna go through some animations. We are now looking at this area where green is the highest value in the visible, so the field is green. And the near infrared band is pretty high, and the red edge band is somewhere in between. So we're looking at healthy grass. Here is June. This one was February. Oh, actually, this was like California, so they have a really good season for this kind of applications. This is June. You can see the highest value now is red, and the near infrared band is much, much lower. So we're looking at soil. And maybe there is a little bit of near infrared band, so maybe there is something starting to grow. And this is September, same year, eh? Still what is 2010. Now it's September, and we have near infrared band high, the green is the highest value, but this near infrared is much lower than this one, so they rotated the crop. So in March they have something, in, what is that, September they have something different. And then again, red is the highest value, there's no near infrared. So in December there was nothing in that field. Probably they just started to plant stuff for the next year. And again, high, very high near infrared band, somewhere in between, and so on. So just looking at the spectral signature, you understand there is a biannual cycle. And you don't need any machine learning there. You just need to analyze the data, understand the data, and how it was collected, the angular information, the AOD, and all the other stuff that I talked about earlier. Validating ACOMP has been really fun. We traveled across US, selected some areas where we were able to go there with a spectrometer, take measurements. We had to identify like areas where you get most of the time that it's sunny, so you don't have too many cloudy images. So this was a pretty big effort. But again, when you use surface reflectance, you want to make sure that things are corrected. And there's a skateboard park here, for example. Bike park was really nice because we went over here, and for some reason, people didn't like this place because everything was really dark and used. This was really clean. For some reason, people didn't go there for several years. And so we were able to take very clean spectral angular measurements. And we were able to collect 5,000 samples, 14 types of different targets. And this is, for example, it's a tennis court. And I don't know if you can see those dots. That's where we position this spectrometer so that we can take angular measurements and we can create something like this. And once you have something like this, we can see if ACOMP is accurate or not. And we have reports with many, many measurements of this. This is like sand. Sand is really interesting. Those were like beach volley, so people play there all the time during summer. So the dunes are different, and so the shadows are different. And so often when you play volleyball, you water the sand because it's hot. And so that's why there is more variability here than other measurements. But it was fun. And that's it. Let's start with part 3 now. Let's see if this works. Okay, we saw the radiometric accuracy, how we do calibration, and now we're gonna do something similar, but with respect to geometry and collection. This part is probably gonna be quicker than the other, so we might finish a little bit earlier, and so we can have more Q&A after. This is the agenda. We're gonna see, issues with vector extractions, and what are the implications of using different DEMs, degeneration models, and what kind of application we can have when you have accurate geometry. You guys are familiar with OpenStreetMap? Yeah? Okay, great. So generally, things are pretty well aligned. There are people manually digitizing all those roads, for example, and for the most part, things align pretty well. But then you get a new collection, and it looks like this. And for example, let's say that you create your labels over every single rooftop in Rome, for example, here in Benevento. And then you get a different collection, and you open the labels, and the labels are all shifted. And then that is going to be really, really difficult to train any model, right? What is going on here? Any idea? Yep.
Most probably it's a constant shift in the GPS they were using and
So you're saying that the GPS, there was a change in the GPS. Is that what you're saying?
systematic error, which is a constant shift in the whole network that they were collecting.
Okay.
That's what they were using for collecting the road. So it's like a constant shift.
There is a systematic error, but it's not in there. Yeah.
Because it is a volatility kind of job. We don't know which base map they have used for the digitization, and where it is aligned also, maybe the base map may be different. So because of that, misalignment might happen.
Yeah, I think more or less we understand what's going on here. I'll try to formalize that a little bit better, try to give you some visuals about why this is happening. But again, in general, don't forget that sensors look in different directions. There's a huge implication of where things are. OpenStreetMap also offers a very nice tool, imagery offset, where you can change the base layer so that you can realign stuff, so that you go from here to here. But that doesn't work all the time. For example, if you're on the Himalayas and we have 2 different images with some vector over road, you can see this is kind of aligned, not really, but not too bad. And here it's like really bad. Yeah, the right one seems stretched. Look at here. But also here, it seems like someone went there with like a finger, like just like smearing all the colors. Can we say if one is better than the other? Yeah, probably this looks more aligned, but they're both wrong, or maybe not correct. If you do like an imagery offset, this is probably the better one, but we're about like 30 plus meters. So there is something fundamentally not correct. And what do you do here? Do you move the vectors in this image, like over here? Should we update the vectors? Like if you were like an OpenStreetMap operator, like would you change the vectors here? Or would you change the vectors here, for example, to align a little bit better on this one? Like, why are both images wrong? Or are they both wrong? Or what would you do there? Yep.
Maybe first not take the native looking image and then take the rest of that specific.
You're going somewhere. I think if he mentioned like maybe use the most nadir image, that would be better. I will probably do that. Often, especially on OpenStreetMap, you don't really know what the acquisition angle is, but that's definitely what you should try to do as a first step. I'm going to try to explain you why. Okay, so this is a satellite. This is the geoid, and so when you project the image in ladder long, that's where you're aligning your data to. You also have a DEM, a digital elevation model, and there are many versions of that. And once you know the pixel coordinates, if you can derive like the latitude, longitude, and height, and everything looks pretty good when you look straight down. There is basically no any real error. But what I mentioned earlier is that we can collect off-nadir angle, like really daily, like that's the normal operation. And often when there is like some disaster and you really need to collect any data because any data is better than no data, we really open up the collection geometries. For example, we might be over Canada collecting images here in California, in Florida, or this other way around. Like, we really like try to steer the satellite as much as we can. And when that happens, we can get very, very extreme collections. This is Mount Fuji, pretty normal collection. But we can get something like this. This was collected, I think, like 1 or 2 degrees above the horizon. And I don't know if you can see, maybe here on the TV is better, but this is China. Those are the mountains in China. And we can kind of like see under the clouds. So this is a very extreme collection. They don't happen every day, but we could collect a 1 degree of nadir. Sorry, 1 degree elevation. So that's just an idea of what's going on here. We collect very far away. This is the mountain, but this is the reference model of the Earth. And so the projection here makes you kind of like dizzy. No, this is produced normally. It's like a camera at the end, right? So you do the image reconstruction. There is some manual process there because those are really, really extreme collections. But it is possible. I mean, these colors look pretty reasonable. There is some vegetation. I know that you cannot see the colors on the screen, but if you look here on the TV, there is some vegetation here. There are clouds. Things look reasonably normal, as if you were on the airplane. And we're going to distribute those slides, so you're going to be able to see that better. What happens when we are off nadir? That's where things get really interesting or complicated, depending on point of views. If the DEM, the digital elevation model, is accurate, you project this point here and everything looks great. You have no issues. But if you have a DEM that is not very accurate, like in this example, this ray that should be projected here, it actually gets projected here. And so if your DEM is not accurate, now you're saying that the point that's there is actually over there. And the more of nadir you are, the worse that is. So here we have the same inaccurate dam, and the more of nadir you are, the more this point, it's really this one, gets projected to a different location. And so that smear that you have seen earlier in that image is part of this. Like the Himalayas are very high, right? And if the dam is not super duper accurate, as soon as you're a little bit off nadir angle, you start seeing these effects. And because the Himalayas are so high, like anything slightly wrong gets projected in the wrong position. And so things that are like the size of a car get smeared across many, many pixels. That is exactly what was happening here. Sorry, I'm going back. But this is what we see here. And again, it's not very clear. If you look at these images, it's probably going to be better once you get the slides. But what you get is you start stretching the 2 or 3 pixels that you collect over a very large area. So if you see something like this, it's pretty normal when you have like big, big mountains. And again, the more of nadir angle you are, the more you emphasize that. So if you want to do collections and you want to do analyzation of the data and labeling and things like that, the more the more nadir looking sensor and collection that you can get, the better it is. Otherwise, better you have a very, very good accurate dam. So dams are not perfect. That's our reality. Like create like very, very accurate dams is not easy. But that is one of the main sources, if not the main source of error. There are also like a couple of different concepts here. There is absolute accuracy, meaning that this is the point that you want to measure. And because the dam is not accurate, you have some different projections between this point and these 3. There's also the relative accuracy, which is basically one time your ray is over here, and another time in another collection, the same point gets projected here just because the viewing angles are different. So let's say that, for example, you are collecting a stereo image. So do boom, boom, collect 1 year, 1 year, and the difference of the same point could be this one. Just because the dam is not accurate, you are collecting from different viewing angles. That is generally called a shear. Now, one thing to see here is that you have perfect attitude and ephemerides. This is basically saying that you know exactly where the satellite is in space, flying, and you also know exactly where the camera is pointing to. So, don't remember how many kilometers per hour satellites go, but they're going pretty fast. And you need to know exactly where you are and where you're pointing. Those are attitude and ephemerides. And those are instruments that we use, for example, star trackers. Star trackers on board, there are like sensors that look at where stars are. Based on where we see the stars, we know where we are in space. Those instruments are not accurate. There is a lot of uncertainties of all those orbits. So because of these are not accurate, this point here, the convergence point, might look more like this, where, more or less you know where you are, but not precisely. And because of this, even if your dam is absolutely perfect, because of those uncertainties, you still have absolute ortho accuracy error, and shear. So solving the dam, doing a perfect co-registration, I don't know who I was talking to earlier about that. Even if you do a perfect co-registration, you still have issues like that. Those are not linear. So again, make sure that you understand those concepts when you try to align your vector of rooftops, for example, when you're doing machine learning. Try to understand those geometries and what are the uncertainties of those collections. So those are the two main errors, the dams and the position and pointing of the camera. And one thing that's really interesting is that when you add those two together, you can see that even if your absolute error, this one, is, for example, I don't know, 2 meters, the shear can be greater than 2 meters. So the position of the same point between two different collections can be greater than the absolute accuracy. When that happens, for example, when you're doing mosaicing of two images, you might see that roads don't align. And there's a very sharp difference between the two, especially, for example, bridges or something like that. You might see those effects, that the same point is not in the same position in both images. There's a very, very crucial implication, again, when you do labeling. You need to make sure that your label align with the data. Otherwise, you're not going anywhere. How can you reduce or minimize the error? You just collect anything and nadir. That will solve several issues. But again, that will really limit the collection capacity. And again, often when there is like disaster and you want to collect anything, you are going to be opening up all the collection geometries as much as you can. And even like 50 degrees of nadir, it's a fair game. So you need to be prepared for those type of situations, especially because time really matters. What else can be done? We often use the SRTM dam that was built in, I think, the 90s. It's a 30-meter posting. It's not great, but you get global coverage and decent accuracy. Ideally, satellite operators can also use their own images, and that's also what we do, for example. We build a 3D model of Earth, and we remove all the landscape, and we just leave a bare Earth. That is a more accurate dam than what we can get with the SRTM. You can get about 0.5 meter posting, so every half a meter you get 1 pixel. We can also use the same 3D model, and we can use that 3D model to do a co-registration using classic photogrammetry between a 2D and a 3D model. In this way, we can backtrack the pointing and orbit uncertainties, and so we can have a much higher accuracy, geometrical accuracy in the data itself. What are some applications? Why it's important to do that? Again, it's a time series. Over here we have, I don't know, 10 images maybe over Nigeria between 2010 and 2020. And I like to look at like points, like intersections, for example. These images have been aligned very well, or as good as we can. And there is no much movement of things, like the roads are pretty stable. Once you have something like that, then you can start extracting road vectors, for example. and you can map the urban growth of this town, this city, just looking at roads. But you can only do that if your data is aligned. If it's not aligned, you're going to be in so much trouble. It's going to be so much more difficult. In this way, you can treat each pixel as a stack of images. And so, for example, when you train a model, you can also include many more pixels and see the stability of the pixel through time. If your roads, if the roads like move, your pixel will not be stable. So you can do maybe like a one image, single image road extraction, which will get you, I don't know, 60, 70% accuracy. If you include a time series, your road network extraction will be a lot easier. You can reach like 95, 98% accuracy. Okay. This is also going to be interesting. It's just mostly applications, and we're going to be doing some machine learning in here, but again, mostly just to illustrate what are the issues that you might find when dealing with high-resolution data. There is a trade-off between resolution and performance. If you are trying to find cars and you have a 5-meter resolution image, you're not going to find any cars. You're probably going to be finding buildings or big structures, but you're not going to be finding cars. So there is a point where objects can be detected only if you have the right data and the right resolution. And maybe instead of talking about analysis-ready data, we should be talking about application-ready data, which happens to also start with an A, so it's very convenient, so you can keep the acronym ARD. But really the concept is drastically different. Okay, let's start with this. We have been talking all morning about the pointing agility of the satellites. This is just an illustration to show that if you're off nadir, your pixel is like this. But the more off nadir you go, the more your pixel will be bigger. And so your resolution will decrease. And for example, if this is the relative GSD, so let's say you have 30 centimeter satellite, and if you are about 45 degrees off nadir, you don't have any more 30 centimeter data, you have 60 centimeter data. So you lose resolution. So if you have a 60 centimeter image, because it was collecting very off nadir, your car counting model probably is not going to work. Like, you don't see a car anymore, you see a blob, and your model has probably never been trained on that blob. This is kind of like the target I was talking about earlier, that these kind of patterns are very common on Earth. They're man-made, obviously. But those are used to check the several factors of quality in data. This is what is called an MTF target. It basically shows, it is used to measure the sharpness of an image. You want to have better, maybe a contrast in an image. You have a very bright surface and a very dark surface. What is the edge there? And so if your edge is very, very smooth, even if your data is, 50 centimeter, the discrimination power of your lenses will not be able to distinguish between smaller objects. So it is not just about what is the GSD, what is the ground sample distance, like your resolution. It's also like, what is the sharpness, what is the resolution power of your instrument. And generally, companies and space agencies, they use these checkboard patterns to measure the MTF and to apply what is called an MTF correction. So it's basically like a very simple kernel, generally like some non-linearity towards the edge. And you will increase the perceived sharpness of an image. You're not going to create new details, just the image is going to be looking sharper. And see Mercedes here. No, she's not here. But many of the applications that we have seen, many of the applications like super resolution that are available in, oh, there she is. Many of the applications that we see of super resolution is actually mostly just like a sharpness increase, which is different than resolving smaller features. You can use, for example, these, which you're not going to be able to see over there. It's going to be better on the screen when you guys get the slides. But those are straight lines. They're 1 meter apart, and then 90 centimeter apart, and then 80 centimeter apart, up to like 10 centimeter apart over here. So anyone working on super resolution or sharpness or increase the sharpness of images, make sure that you have some data over here so you can actually measure like the super resolution of your model or your sharpness, the sharpness of your image and the camera that you're using. Anyway, this was not really the topic I was trying to talk about. How do you simulate multi-resolution? This is really crucial for when you are training models. For example, model was trained on 30 centimeter image, might not really work if you have a 50 centimeter image. So one thing that people do is to simulate a 50 centimeter image so that you can train your model on 30, 40, 50, 60, and so you have a multi-resolution model. This kind of approach is also good if you're doing super resolution because you can simulate different pairs of high res and low res and also be able to train a model for that. What people normally do is just apply a bicubic downsample or, I don't know, something maybe a Lashkosh or something very simple. You just downsample the image and call it off. That is not what a satellite sees in space. It's really, really different. If you have an aerial image, you need to have at least 2 or 3 times the resolution that you will really like to simulate because you want to account for the nonlinearities. So if you use a 10 centimeter image, you might be able to simulate something between like 25 and 30 and above, but you should not really simulate anything like 2x. The first thing you should do is to estimate the MTF. The MTF, again, is the transition that you see here. Why do you need that? The MTF is in Fourier space. You do the inverse of that, and you get the blurring filter. That's basically what it is. This OTF is the kind of like the inverse of the MTF in space. At the end of the day, it's just like a blur filter. You want to blur your image first. Do not just do nearest neighbor resampling and calling it off. You need to blur your image first. When people do comparison of super resolution images and they compare like an aerial image downsampled to a super sample product, they will see difference because the downsampling doesn't represent what a satellite sees or an aerial platform sees. And I've seen that done at space agencies where I went head-to-head with people making sure that they understand the physics of what they've done, because I've seen reports that were completely with flows, that they were completely wrong, but physics is important, even when you do machine learning. Once you convert and you blur the image, then you can apply a resample, and you can pick the flavor you want. Bicubic generally is decent, allows you to have some nonlinearity at the edges. Lashkosh is probably better. It's a little bit more compute intensive, but generally represent better the image. Other things that you need to add is noise. Images are noisy. There is the atmosphere. right? If you have an aerial collection was acquired a few kilometers above the ground, you don't see the entire extent of the atmosphere. So add noise, use Modron to simulate what the noise is from the ground up, add compression and decompression. Sensor in space, apply compression so that we can send the data down to Earth and the data is decompressed. That introduce some artifacts. So when you do simulation, make sure that you account for compression and decompression effects. Finally, the MTF that you calculate here, you need to re-add that in the image. You remember you blurred the image here? You need to re-increase the sharpness because of this. And so the MTFC, C stands for correction. The MTFC correction is an important step when you do a simulation of the data. And at the end, make sure that when you do this simulation, objects make sense. If you have, for example, a soccer field, you know that there are measurements that you can take. The lines have a meaning. Use those, for example. Or if your car measures 30 meters, probably something not correct unless you have a very, very, very big car. It seems trivial. Don't laugh, but I've seen that. So I usually use this, like it's a physics-based protocol. And there is physics, there is Modron in this. You need to know what kind of atmosphere you are trying to simulate. This is not just a simple resampling. We talk about MTF-C, the correction. This is before and after. You can see this image looks sharper. It is not super resolved. This is just a very simple sharpening kernel. You can use an unmask where you have, for example, 5 and all -4 at the edges as an example. Something very, very simple. Sorry, -1. You can understand what is the real MTF and create the right kernel, but it is important to add again the sharp looking of an image. Otherwise, you're not doing a fair comparison. Again, if you have this a football field, but you know that those, I believe, are like 1 meter away from each other, 1 yard away, I guess. So that you know that this is a high resolution, this is not. So make sure that you do those checks. Then you create your multi-resolution data set, right? And you do this starting from example with 7 centimeter. And you can simulate 30, 40, 50, 60. And what I said earlier is that you should have at least like a 3x factor. So we could not simulate a 15 centimeter image with a 7 centimeter aerial. You could, but it's wrong. So don't do it. So we simulate, when we say native, it's native simulated from this. We also have like an HD version of our data. That's what we applied. So we use the 30 centimeter to create a 15 centimeter product. What I was trying to say earlier is that you have this beautiful car here, and here you don't really know what you're looking at, right? You can probably think this is like a trash can and this is a scooter, right? Like you just don't know. You cannot resolve this object unless you have more information at different resolutions. So resolution and sharpness really matters when you want to do object detection. We use YOLT. You guys ever heard of YOLT? Do you know YOLO? Yeah, of course. You only look once, right? This is you only look twice. It's better than YOLO. At least it used to be better than YOLO. I don't know. YOLO 8 looks pretty good, 9. But YOLO 3, 4, it was not very good for remote sensing. The reason is that YOLO was developed for cats and dogs, where you have your cat or your dog that occupy the entire image, or most of the image in a picture, right? Remote sensing, you might want to detect one car, and so you're looking for like very, very small objects in a very, 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 very big image, especially if you're doing, for example, anomaly detection. So this is an open model. It's based on YOLO, but you look twice. And the twice is because the second pass that you do a better job in detecting smaller objects. So if you're not successful with YOLO 4, 5 framework, give this a try. It's open source. We have pretty decent success with that. Anyway, we have this multi-resolution data. Some is native, simulated, some others HD. But bottom line, what you see here is that if you want to detect cars, don't use 60 centimeter because you're not going to be very successful. It is really, really hard to detect cars at 60 centimeter. You need to have at least like 50 or 30 if you can. What we did here was to retrain each model on each resolution so that we can do like a fair comparison. So we didn't train on 30 and then test on 60. We trained on 60 and validate on 60. Couple other things interesting. 30 centimeter can get you up to some point. Ideally, you want to get to over 90 with 7 centimeter. There is a kind of like plateaued here. It's not that 3 centimeter or 1 centimeter will get you a much better model. And at 1 centimeter, you're using really, really large images. So you need to understand what is your trade-off between using ginormous images and what kind of accuracy you want to get. Again, 30 centimeters is probably a sweet spot for cars. So for something in the order of a few meters, a couple of meters. Another interesting thing, which is something that Mercedes talked about on the first day, is that generally, HD images, they perform better than native resolution images. And what it's kind of interesting here is that if you see this as a linear relation, the HD product is somewhere in between. So it's not as high as a native 7 centimeter, but it's better than 30. So there is some merit. Actually, there's a lot of merit on what she was talking about on the first day. Obviously, if you're doing super resolution or if you're doing something like HD for building detection or glacier detection, probably you don't need that. Again, every application has the right data. This is just like some visual to cover exactly what I just said, that if you use 7 centimeter, you get very, very high accuracy. I think there was like one card that we missed somewhere. Maybe it's not in this image, but and then the lower resolution you go, the more errors you get. In this case, we didn't detect that car. And we also like more false positive if we were at 60 centimeter. But again, 60 centimeter, you get a blob. And that blob can be a lot of objects, for example, a trash can. Okay, we talk about analysis ready data, and we're kind of like switching gear here. So I think application ready data is probably more useful. And I was talking to someone earlier about there have been like many, many efforts in the community to create an ARD standard. And unfortunately, I think we're very far away to have a standard. And the reason is because your application is different than mine. And I'll show some example after, but CEOS is, I believe, what NASA and ESA use for Landsat and Sentinel. It is one flavor of ARD. It is not what other providers use. And you kind of like the extreme here. You have raw imagery and you have fully harmonized data. And fully harmonized data means that if you get a Landsat collection, it will look identical or as close as possible to Sentinel and vice versa. This is what harmonization means. And somewhere in between, there is this ARD process. On this part, you basically have no calibration. Like, we talk about radiometric calibration, and so if you have raw data, you don't have that. On the other side of an ARD protocol, we talk about using, for example, surface reflectance and have aligned data. So those are the two extreme, but I'll show you next how those two extreme doesn't really matter. Sometimes you don't need super calibrated data. Sometimes you don't even need colors. You don't need surface reflectance. For example, you're trying to detect airplanes or cars. A really accurate radiometric calibration is not necessary. You're using black and white images. It doesn't matter. And you're on this side of the spectra. But if you really try to understand if this is like a pitched roof, or if you're trying to analyze large temporal series of images, then you really need to have like surface reflectance. Otherwise, again, you're not going anywhere. This is another example of like pitch roof where you get this, and what I think it's interesting over here, you have very bright hotspots. The reason is that this is not only a white pitch roof, but it's also metal, so that the sun reflects towards this direction. So you cannot understand that if you don't have very accurate surface reflectance. But again, here you don't need surface reflectance. Because of this, it's really hard to talk about ARD. It's really hard to say your application is more suitable for an ARD type of product rather than mine. I was talking to someone earlier about detection like small objects, and what is small? Like, is like a scooter small? Is a person small? Is a tank small? An airplane? What is small? So there's also like another aspect, and here we are moving now toward the insights. There are different markets, like different people, different users. And for example, in the one targeting agriculture or maritime applications, people are really, really familiar with data and satellite, and they really want to have the most accurate, the most calibrated data that they can. And generally, they really want the rawest form of data. Like, do not touch my pixel, I'll do everything by myself. Don't even look at my pixel. Then there are other people, like new markets, like insurance or finance. They don't care about pixel. Like, that's a pixel, what do I do with that? No, I need to know the information so that I can take some measurements. And information at the right time is the only thing that's needed. If I tell you that, hey, it rained like 3 days ago, I'm like, okay, it's too late now. So the timeliness of some of this information, some of those insights is really, really key. And there are different type of customers. You know, if you're like civil government, industry, intelligence, your goal is different than mine. And we have different missions, timelines, requirements, and also like different skill sets. So again, if you work for an insurance company, you might really don't care about if the data is calibrated. You don't really want to see pixels at all. You just want to have the final product. And so depending on where you are in this information chain, you might want to get different type of characteristics, different type of ARD. In general, like a data set can be, characterized by different qualities. For example, the quality of the data itself. Like, how accurate is my measurement? Like, if you say that the NDVI is 37%, it is actually 37%. Have you done your homeworks calibrating the sensor? Other people don't care about that. They want to know if the data is available. This is a disaster. There's a flood situation somewhere. People are strained somewhere. I need to have the data now. I don't care about quality. I don't care, if you're calibrated or no. I need the information now. And I need the information available now. I need the information available on my iPad. If you put that on FTP, I don't know how to get that from my phone, right? I need the information available here on my phone so that I can go on the field and rescue those people. And often data need to be interoperable with other data sets. Like, you have aerial from, again, there's a flood situation somewhere. NOAA is collecting aerial data. You want to have historical data from Maxar, data from ESA, for example. All these data need to play well together. If you align your aerial collection to, for example, Maxar or Sentinel data, then they need to be aligned. That's kind of like interoperability. Here's some applications now. Lane use, lane cover. Like, I've seen that so many times through my career. Everyone started doing lane use, lane cover. But if you're like a telecommunication company, what you see here is not really the map itself, but I see buildings here. So when I'm putting my towers so that you have signal when you're walking down the road, I know the height of this building. I know if someone is building something in front of my tower, because if they do, then I need to move the tower, otherwise those people will not have any service. So the lane use, lane cover map that people have been working on for several years is a completely different aspect for a telecommunication company. Or for an insurance company. Like, why do they want to know that? Well, they want to know because if there is a big tree next to your house and you are in an area where there are like typhoons all the time, that tree eventually will collapse on your rooftop and might kill you. And if I was an insurance, maybe I don't want to really insure you because it's going to cost me a ton of money, right? Or maybe you're like a pool or something that will trick an insurance company to say, I think your premium is going to be higher than what I'm telling you. So different markets, same lane use, lane cover. Also here, consistency of the data is really important. So you want to use ACOM, you want to use surf reflectance. Here we have a time series over forest. And the alignment is really key here because you want to make sure that when you align the data, if there is some deforestation, you don't have false positive or false negative. So for example, if you're an NGO, you might want to look at illegal deforestation or mining, for example. If you are some sort of like company looking to agriculture, then you want to do like a crop analysis. And so you have maybe a time series of data and you want to monitor your crop, for example, and you want to be able to align the data so that you know that you're looking at your own field, not someone else. Road network. I mentioned earlier that if you have a deep stack of images, doing road network extraction is a lot easier. You can really detect most of the roads fairly easily using machine learning. But if you are, for example, Amazon, where you are delivering packages, you want to know if a road exists so I can reach your house, or if a road is closed so I cannot reach your house. If you are in the energy sector, then is a road being built next to my pipelines? Because if they do, I need to make sure that they don't cut my pipelines, right? So that if you're home, you still have internet, you still have gas and stuff like that. So again, completely different markets, but still they have the same need. And finally, like here you're the patterns of life, like people moving, like you have collection through the day, and cars are coming, leaving, moving, and there's a huge traffic jam at some point because they close the border. And you're like data scientist, you're doing machine learning, and you want to use a deep archive of data. In this case, again, we go back to ARD. Like, you need to make sure that you understand your data is ready for your application. Last slide. Doing good on time. This is where we go from imagery to insight. What do you see here? Besides reading here, don't read that. What do you see here? I'm sorry, who? That is, I believe, either a car facility or, yes, I think it's a car facility. Those are like all cars, right? But if you only have like pixels, you will tell me that's a huge parking lot, which it is, right? You are an investor. You have a ton of money. You don't know what you do with your money. You don't do anything with an image. Like, how will you use that? Right? The image needs to be auto-rectified and colored and calibration. They're not gonna waste time on this. This is what imagery is. You can transition to information. Now, you can map every single car and say, well, this is, it's a parking lot. And I know where all the parking lots, they're empty and where they're occupied. Can go maybe like a step further and say, well, there are 10,000 cars here. And let's say this is like Ford, for example, building cars, or Fiat. You know that they've been building cars, and eventually those cars are going to be sold, right? Or think that's, for example, like a grocery store, like a Walmart or whatever grocery store you have in your area. There are a lot of cars parked outside. People go buy grocery. That chain is probably going to make a lot of money, right? That's where you transition from information to insight. The insight is like a prediction analysis where you say, hey, that grocery store, that facility is building cars. They've built 10,000 units of that car model. They're going to be selling those. And so if I'm an investor, all I need to know is how many cars, how many customers are at that location so that I can predict if that facility or that grocery store will be making more money so that they can beat revenue or lose revenue. I need that information now. If I know this for 2 quarters ago, that company might have crashed and lost all the value. I need to know this now. If I know this real time, I can do better investments. But this is how you transition from just a picture of a parking lot into something that makes financial meaning. And that's how you transition from just training your model and counting cars to something that's information and insight for another user.